Thank you.
Should I just begin?
Yeah, so here
Okay.
we are. We're back at the recording. Oh yeah, sorry, you were gonna say something.
Oh, no, no problem. Yeah. So we're back recording for the conference. Hello, everybody, again. And our next talk is going to be, I would say, a bit dense in terms of information, a bit new, but nevertheless very exciting. I got a glimpse of this during an earlier meet I had with Lorelai, who is our amazing presenter. Very interesting information, very interesting insights. Lorelai, would you like to introduce yourself? Tell us a bit about yourself, the talk, and you can take it from there. Thank you.
Sure. So I was gonna kind of like introduce myself a little bit when I was into the talk a little bit, just for the pacing aspect of it. So maybe I'll hold off on just like my background, just because I actually was gonna start with the history of the subject a little bit today, just because Danielle said that I could take my time a little bit, and so I'm going to take advantage of that, and I'm going to talk about I'll talk about the context for all of it. And so I didn't mean to go to my background. Can you see the slideshow?
Yes.
Great. So this is the talk, and as you can see, I have a lot of history here. That's what all this stuff is on the left. And I won't go through all of it, but maybe I'll point out some of the overarching themes and why I would want to bring that up in the first place. And I guess I'll just say really quickly before I even talk about brain-computer interfacing in general, is that this is a topic that I think is not only really broad in its basis, but it also has an ethical and just like moral undercurrent throughout all of it. And so I like to begin and end with that anytime I talk about it a little bit, just because I think so often, especially with this technology, it's really easy to get lost in like how it's going to happen and not what it's going to be used for. And there's a lot to be said about uh, all of it historically as well. And so to give a little context for just me talking right now, is that I got encouraged to talk about this subject by Danielle maybe like 2 or 3 months ago, and I hadn't really pursued data and Clojure just yet because or brain data and Clojure, because I was still kind of like learning. I was in a learning mode. I was just like, I'm still reading about all of this stuff, but I got really encouraged by SciNoj, and so that's been really great. And I'm thankful for all of you to give me this space today, and I am really excited to talk about all of this because I've been thinking about brain computers for a really long time, and uh, during this process, I also began a separate thread of research in practically applying brain computing with an actual device that I have behind me, which I might show since I have a little bit more time today. I'm kind of taking a long time to get to the actual point I'm trying to say at the beginning here, but what I basically am trying to say is that during the Reclosure talk, I'll be talking a lot more about the history and the ethics of brain computing. And today, I'm going to kind of gloss over those details, but I do think they're super important, and they're like an incredible motivating factor for why we would be interested in all of this. And so I'll start by saying that I think brain computing is the actual goal of all of computing in a certain sense. because if there is really a goal for computation, it's to be able to do it at the speed of our thought. And brain computing is inherently discrete while our minds are continuous. And I'll kind of talk about that a little bit too. But it's becoming so available and accessible that you can essentially make it feel continuous anyways. And so this is brain data and Clojure, and I'm thinking about brain computing as broadly as possible, as always, because I don't want to limit the actual technology. I'm really interested in combining software and hardware into systems of brain computing potential, essentially. And with all of that, that's all like prelude to what I'm about to say, because I'm about to just jump into brief history and then I'll do the talk. And so I'll jump into the slide, I guess. I was kind of hesitating to do this because it's a lot of material, but I'll go really fast. So this is where this paper is from. And if you're interested in finding it, I could give you the link for all of these. Oh, actually, before we jump into it, I should give you all access to this. This is, I'm going to be referencing like a lot of different materials today. And so I'll share basically everything that I'm talking about. Let me move this off the screen. And so this is my spreadsheet for all things brain computers. It has all of the things I'm going to reference today plus more. And this will be something I talk about right after I talk about the history really quickly. But these are different types of brain-computer interfaces on the first tab. The middle tab is a tab of all the resources, which is just like short snippets, and then just some other notes and references on the last page that are just kind of interesting. So that's just kind of to look at. And I'll also share a couple other links as we go, but I think that that'll do for now, and we'll jump into this. So Hans Berger was the person who made the EEG, and interesting life. I don't want to go too into the history, but I do want to just point out that he was a firm believer in psychic phenomena and telepathy. And I just think that that's so wild because like it's this like really far out idea that humans could communicate that way. And this person saying it in 1920, and he ends up being the director of a hospital and inventing the EEG, which is just one of the most widely used neuroscientific methods of analysis on the brain in general. And it wasn't like a small part of his life that he believed in psychic phenomena. Actually, he actually was such a believer that he like studied that phenomenon through his entire career. And that's just to note that he was a really interesting figure. I have a lot more to say about him, but I'm going to just skip through. This is some of like the first EEG ever here, and another reference. I'm going to skip through some of these things because there's a lot of really good stuff in here. But basically, there's Hans Berger, who's like this incredible researcher who comes up with EEG, but he's like a little bit of a weird dude, and I'm not going like super into this right now, but also like possibly a Nazi. It's actually unclear in the records, but it seems like he at least didn't support the Nazis, but he also didn't necessarily denounce them. And so this is like a whole article on just his association with them. And, you know, to me, it seems like after reading about this for a while, that it's likely that this person was not affiliated with the Nazi party, but that he didn't really make that well known, and he lost his career because he didn't like side with them enough. And he was so despondent over being removed from the hospital that he ended up ending his life a short time after he actually lost his job. And so he ended up just leaving this on his mantelpiece. And anyways, I shouldn't gloss over such a like strong story, but there's a lot to cover, and that's just one example of a figure in brain computing who it's really unclear this person's actual character. And I'm going to bring up Charles Bell as well. This is actually Descartes. This is like a little bit of an aside, but there's a really influential figure on brain computing from even before Hans Berger, because Hans Berger made the electroencephalograph, but before him was Charles Bell. And Charles Bell is the person who actually realized that there's a connection between the spinal cord and our brain and the rest of the body. And the way that Charles Bell became aware of this, well, the way that he like tested his hypotheses was very grim. He tested on live animals without anesthesia, and he also writes a lot about the human body and the human anatomy. And I don't want to get too into this, but this is like some very poetic writing of his that I just have on the screen right now. And it almost sounds like this person is like really well educated and poetic thinker, but they did pretty brutal things to animals. And I tried to read into this person's history to see if like, well, do they have like remorse over the fact that they're like performing surgery on live animals without anesthesia? And the truth of the matter is that if you read into it, that it seems like not only does he not have remorse, but he's actually like very proud of himself. He views animals as lesser than human, and he actually thinks that it's like his ordained duty to do this. And so if anything, he probably had like some weird like I don't know, just like feelings of duty to do these things. And to me, these are just things that aren't like palatable, but that they're a part of the history of this profession. And so this is some messed up writing, in my opinion, of his experience with those animals. And I won't go into that too much, but this is how he actually did like these early experiments. And it's possible that like this was the only way to find out about these things, but all I'm saying is that I think that this is morally very questionable, and that's not okay. And then I had hidden a little bit of a meme here. So on this slide here, I'm going to delete this in just a second. You have like Hans Berger, who has this like ordained feeling that he is actually deigned to inflict these harms on other living beings. And you have Hans Berger, who just is like a kind of kooky person, but also clearly not like strongly for justice, it seems like, to put it briefly. And so I think that ethics need to be at the forefront of all of this, because the people who are interested in this are not necessarily good, because this is the other person who is interested in brain computing right now. And I have a feeling that Elon Musk cares even less than Hans Berger or Charles Bell about the people who he's going to be putting these systems in. And so that's like the historical portion of it. I just think it's extremely important to emphasize that historically these things have always been ethically questionable, and we don't even necessarily, I feel like it's something that's buried because it's like extremely uncomfortable. It's pretty dark, and the thing is that now it's kind of this weird conflict, because like everything is so standardized. Like there's no more cruelty really. There's a lot more ethical standards that are held today, but there's still a lot of research that's going on now where consent is just such a huge topic. And I probably lingered on this too much already, so I'll move on from that. But just where I like to start with all of this stuff always. And so when it comes to this talk, I mean to be as much of a guidepost as possible. Brain computing is a discipline that's extremely wide in terms of the fact that it's got lots of different manifestations, such as EEG versus like MEG versus fMRI or any of the other technologies. So it manifests itself in a lot of different ways. And then even inside of just like EEG, there's like a whole world where people have entire careers just reading EEG data and interpreting it. And that's not my forte, for example, but it's something that I'm interested in, and that is inherently a part of the project that I'm doing. So I'm here to be like a guidepost to kind of point people towards resources, hence the reference sheet. And also I mean to like bring up topics. But for this, I was going to try and stick to data as much as possible, but then I was offered the chance to take my time a little more. So I just wanted to do the introduction slightly, which I wasn't planning on today. Today, I was really going to focus on, in practice, like the collection and the recording of brain data. And so that's what I'm going to kind of get to here. This is a really cool video that I'll just share. I'm not going to actually play it right now, but I'll just put this in chat in case anybody wants to watch it later. This is Krishna SciNoj, who is actually working for Neuralink, which is that was Elon's Musk. Well, Elon Musk actually bought them. But Neuralink is basically one of the leading organizations that's doing this right now, and they have a lot of pretty advanced technology already. And this is Krishna SciNoj talking about what they've done for like an hour and a half on handwriting with brain computers, which is really interesting and fascinating. Unfortunately, he passed away a couple of years ago, but a very compelling speaker, and it's a really interesting video. Okay, I'm going to gloss over what is a BCI really fast, because I'm going to try and get to the actual data. And so there's a lot of different forms. I have this ordered from least to most nefarious, is how I've been thinking of it, because deep brain stimulation is actually one of the oldest methods of brain recording and brain stimulation in particular. This is used to stimulate very deep motor nerves for motor disabilities like Parkinson's disease, and this is also used for cluster headaches and epilepsy, among other things. So this is actually something that has been in place for a while. It's got a very high success and healing rate. And then you have cochlear implants are considered a type of BCI device that augments hearing. And that idea of augmentation is a crucial part of everything, because in the BCI reference sheet, you'll see a book right at the top here, Wolpaw and Wolpaw, Principles and Practices. And this book here actually lays out 9 different categories of brain computing. And I actually should be able to pull this out if I go to, this is just a regular expressions PowerPoint here. Sorry, let's go to this right here. And so you'll see that they actually have 9 different categories. This is directly from Wolpaw and Wolpaw here. And so they have enhance, supplement, replace, restore, improve, contribute, design. So I said 9, but this is actually 7 different categories of different ways that brain computing kind of tries to do what it does. And so when you're thinking about sorry, I just lost my train of thought. A cochlear implant, you're talking about something that's actually enhancing the, all right, that actually would not fall under enhancement. That would be to replace. So that provides an alternative system for performing a loss function. And so these are classifications of different types of BCI. And so let me turn back to, and I apologize for any background noise. Let me turn back to this. This is an electrocardiograph, or also known as a Utah array. they look like this. Oh, these are actually the neuropixels. There should be an electrode array. Is it behind there? No. Okay, I actually have a picture of them over here. This is what a Utah array looks like in real life. So you can see that this has a 10 by 10 grid of electrodes, and that's just placed on the surface of the brain. And each of these can actually record, like, I believe this type can record up to 16 channels of data on one pin. So this is, I think it's 512 is what it comes to. It's like one of those math or one of those computer numbers. Anyways, that's a Utah array. So these are all just different forms of BCI. And so that's why I put together this spreadsheet to begin with, is because, oh, this is the schedule spreadsheet, whoops. That's why I put together this spreadsheet to begin with, is that the technology exists in a lot of different manifestations. I was saying that. And so I'm focusing almost entirely on EEG and my exploration of this technology right now, the reason for which is this low price point. You can kind of use this as a reference to compare and contrast the cost benefit of each technology. And you can see that most of these systems are wildly expensive, hundreds of thousands to even millions of dollars on the high end. And just recently, EEG has come into consumer range of costs. However, if you actually turn your attention to the OpenBCI website, which is actually what I was getting that price from, their prices have since increased due to tariffs, of course. So now it is no longer $500, but actually due to US policy, everything has gotten quite a price increase and is now up $125 more to consumers. And so that's what is going on with that right now. But still, $625 is a lot more reasonable than some of these other costs. And you can do pretty cool stuff on these budgets. And so I happen to have one of these devices now, which is pretty amazing. I have it right here. This is what it looks like in real life. You can kind of see it there. And if we were to check it out on the website, it's right here. And so I'll zoom in on the picture here. So you see it's got 1, 2, 3, 4. It's pretty much as simple as that. These are 4 data channels. And then this is a reference electrode, the ground, DG, and then AVDD. Maybe someone here can tell me what that is. I'm not sure. You don't even really need to know that much about the hardware, because it's really 1, 2, 3, 4. You're just worried about these input channels. And so that's what I've been working with there. And I'm kind of like jumping around a lot because I was told I can pace. But anyways, the most nefarious version of BCIs actually is just cell phones and computers, to be honest. And so I basically make the argument that those are brain computers inherently, because what else is it other than our brain issuing instructions to the computer? It's just that right now we have a 2-thumb bandwidth with our cell phones. And so the idea of brain computing is to not do anything new, but rather to issue the commands in a novel way. And so like the actual idea of like interfacing with a computer is something that we're all extremely comfortable with. It's just the medium of the interfacing. And that also brings up this really interesting point right on this slide, which is that, well, what is a brain-computer interface? It's not really about just the brain. It's not really about just the computer. It's really about the actual interface, to be honest. It's about the thing that's in between the brain and the computer. I'm not gonna like talk about myself too much here, but I am really generalist, which might be apparent, is that I have had a pretty broad background in my life. I went to school for music and philosophy. I did social work, and I also programmed my whole life in a variety of languages. And I love Clojure, which is one of the reasons that I got involved in SciNoj. I'm pretty active in the Clojure community in general, and I'm glad that we get to do this today and that I get to talk to all of you. And so how is it that you like actually start in here? Because like part of this is that I want to like kind of direct people to the different parts of the field, because programmers can have an impact in brain computing in a number of ways. You could be doing this just making actual interfaces between the hardware and like a programmer in general. You might make that like API, but not have anything to do with the actual like application of the technology. Or you could just be like parsing data, probably. There's lots of different steps to the process of making a brain computer, taking that data and then actually doing things with the data, and it's different for every different type of technology. And so there's a lot that goes into it, and this book here is the book that I have in front of me. This is Brain-Computer Interfacing, an Introduction, which is on this screen right here. This is kind of like the entry point for anyone who's interested in this broad domain of brain computing. And so they have a website that I'll share right now. And so this is the Washington University BCI website, and they have the table of contents on here. Now, I'm not going to go into all of this, obviously, because it's too much. It's simply a huge domain. But that's actually kind of the point of the book, is that I just want to show this quote and emphasize it slightly. The multidisciplinary nature of BCI research is a major impetus. And so the idea is that a neuroscientist doesn't really know about design patterns, and a programmer doesn't necessarily know about brains, like, and how neural activity is actually working physically and how we record that. And so brain computing is an actual domain that requires a lot of input from not just programmers, not just doctors, but all sorts of hardware developers, and obviously there's legal input, and there's lots of other tangential fields that come into brain computing. And I, for one, am particularly interested in this public relations aspect of brain computing, which is one of the reasons I wanted to talk about it today. And it's one of the reasons I talk about it so broadly, is that I want to recognize the fact that this is a very complex technology, but it's one that's going to impact all humans. And fundamentally, the way that we interact with computers and technology, it's going to increase the haves and the have-not disparity in the world. And so there's a lot of ethical and social ramifications of these technologies, and you don't have to be a neurologist to work with the technology. You don't have to be a neurologist to have an opinion on the technology. Maybe that having a neurology background means that your opinion might be weighted differently on different things. Like, obviously, not everyone is going to have the equal amount of say in how the technology is developed, but how it's implemented should be something where there's a lot of nuance and thought. And so I'm very interested in tackling this stuff from the most broad perspective possible. You can see I just color coded this. I'm just trying to make it like a little bit more approachable. And I would say that from the programming perspective, we're mostly concerned with pink, green, and purple here. I've talked a lot about Rust red here. And one of my favorite things to talk about is orange, this top left corner. Basic neuroscience is, how do we take a biological signal and express it digitally? That's like one of my, that's what I'm talking about with, like, there's different levels to the process, is you could be a programmer just doing this and not know anything about machine learning. And I have to be honest, I know very little about machine learning. I've been really spending a lot of my time in the green area because this is the most widely applicable. That's actually why I left it the biggest, is that this is useful not just in brain computing, as myself and Danielle have talked about a lot, is that filtering is something that's very cross-disciplinary. And it's actually really, really wild how often having a musical background has played into my understanding of brain signals and how this works. And so just to cut it up a little more, I divided it up into even more, just like these are really getting at the core of what we're like thinking about with brain computing if we're programmers, because different people are going to focus on different parts of everything. And so I'd like to say a little bit about all of these things today. Not go into it all too much, but show where I'm using it in Clojure for sure. And I'll try and speed up a little bit and get there as fast as I
Lorelai,
can.
maybe Lorelai, or maybe
Yeah.
I'll stop you for a moment. Just say that I think time is rather flexible because it is the last talk of the day, and maybe it makes sense to not try to be fast about it.
Sure.
And also, if you wish, maybe if I don't know if that makes sense, but maybe we could take a moment to do something about the background noise. Don't worry about it so much if you don't think it can be changed, but if there is something that could be done, then maybe it will make all of us slightly more comfortable. What do you think?
I really wish that there was something that could be done about that, but unfortunately, there's nothing that can be done about that.
Yeah,
I
no worries. Yeah,
apologize.
just wonder. Yeah, sorry. Yeah, so yeah, just want to say, I think we can, slow down. Yeah, thanks.
Sure. I wanted to speed up through those portions because it was less where I wanted to spend my time today. And this is like my favorite section of everything is this actually extracting a signal. And so this kind of plays into what I was saying about how it can be really intimidating to get into this because it's like this whole new domain, and brains are the most complex part of the human body. They're extremely complex in all beings, and so it's natural to be like almost like, well, I have to like let that be for the experts, but I want to like encourage people to understand, like feel comfortable having like a naive like understanding of how it works, because like the fact is that like there is actually like pretty clear knowledge that has been established just through many years of research. And so like we kind of know at this point that neural activity is what's called a stereotyped event, and that's on this page here. Oh wait, it's actually on the next page. Whoops. But we kind of know what neurons are, and this is like very well established fact at this point. And so the reason I say that is that you don't have to know everything about the brain to actually know just the parts about, well, how are we picking up a signal? And so I'm going to try and convey that right now. And the idea is that I love this description, a leaky bag of charged liquid, because when I first read that, I was like, what is a leaky bag? Like a leaky bag seems like such a weird description of what something would be, right? Like I would think like maybe a tree or something, but a leaky bag. And a leaky bag is really interesting because a leaky bag holds liquid. And that's why it's important that it's a leaky bag and not like a tree or something. It holds an electrochemical fluid inside of it. And that's what a neuron is. It's just a container that contains electrically charged fluid. And it's suspended, the neuron, in more brain fluid, which is this electrically charged fluid. And so here on the bottom left, I kind of like colored a little bit. You have this is the lining of a neuron, and these are called ionic channels. That's one of like the buzzwords that makes it seem like really complex, but all ionic channel means is that these ions, which are responsible for the electrical charge, they can pass through this, whereas this bilayer lipid membrane, this can't be passed through. And so these are the leaky aspects of the bag, or the ionic channels. And when there is neural activity, these chemicals are passing through these membranes. And what we're actually recording with most brain technology, not all, but most, is that electrical activity. And that's not the case for everything. But for EEG, we're picking up the electrical signals that are happening here. Now, I use the word stereotype event. Where is that? It's probably on the next page, because that's really like the key thing. shows, I'm just going to skip ahead to stereotyped event. Oh yeah, here it is. Okay. Information is thought to be conveyed by the firing rate of, okay, I'm going to go back really quick. Sorry. Back to this page really quick, is that I was just saying that like you have these ionic channels where there's like electrical ions on either side of the neuron, and they can pass through here, and that's what we're actually observing. And so when this happens, well, I write it here, the rapid influx of Na+, this part's not important, but this exhibits a sort of all or one behavior. And that's really the key point, is the all or one behavior, because what that means is that in the firing of a neuron, when one neuron sends a signal to another neuron, when that happens, there's no information thought to be conveyed in that firing, but rather it's the firing itself that we're recording. And so it's considered a stereotyped event, and that means that it's a binary signal. So there's a flashing of the neuron. It's just going on and off really, really fast. And that firing rate is what's being recorded. And we turn those into waves, and we model it as 0 or 1 digital output. And that's where computers get involved. I won't talk about synapses. I know you said I could take my time, but this is definitely deeper than is necessary. Synapses are just what allow for that interneural communication. And you can see that they have these like particular channels that allow what are called neurotransmitters to pass through. And neurotransmitters essentially will, based on what the neurotransmitter is composed of, because that's like a collection of these ions essentially, they will go on to do other things, and some of them might not even pass through all the way. There's lots of different things that can happen in these pathways, of course, and that's where it gets really wild. We're at brain organization, anatomy, and function. And so I'm going to talk about the sections of the brain really quickly, but not in the way that a lot of people really like have been taught it in schools, I feel like. Because like I think that one of the things that we think of when we are taught about the brain is we get those colored pictures of all the different regions of the brain, and those are great pictures. Those are really helpful to like chart out what do you call it, like the actual sections of the brain itself. But I'm interested in showing you all the 10-20 system, and I thought I had the paper up here, but I guess I don't. So let me just see if I can pull it up on another screen. Sorry, I thought I had this one ready. 10-20. Okay, I actually don't have the academic. I had a nice academic paper ready. I think it's in the BCI references, but this is the 10-20 system. There's also a 10-10 system, and this is actually the 10-10 system right here. And so when I say brain organization, like this is exactly the type of colored chart that I was talking about. This is like helpful. It's one way of thinking about the brain. But as programmers, we might want to think of it as this like array of electrodes. That might be the most helpful thing. And so this is arranged pretty apparently on the head. This is a nose at the top, and it's a little bit of a silly drawing, but this is actually pretty internationally recognized like schema that neurologists will use to like point out what different configurations they're using for electrodes. And this is all EEG I'm talking about. This is only EEG, which is wild that there's so much to say about just one thing. So you can see that they all have numbers that go up as you get away from the center of the brain. And you can see the left side of the body is odd numbers, and the right side of the body is even numbers. And that as you go forwards and backwards, they have different letter identifiers. So it's frontal. I'm going to mess it up, of course. I'm sure it's frontoparietal, and then like AF. I'm forgetting the A word. These are pretty. It's so wordy, you know, the whole discipline. I get tongue tied or whatever. Well, it's ancillary. It's like one of those words. It's like ancillary or whatever. I normally just say A in my own head because I'm just like dealing with the actual sort of placement more than worrying about the actual words. Because it's like parietal, occipital, and stuff. Anyways, this is just literally charting the electrodes to places on the head. And the important aspect is that these are percentage markers. That's why it's called 10-10. You can see that there's an array of 10 here. They're all separated by different ratios, and those are polar ratios because it's like three-dimensional. It's like going all around the scalp. So those are standardized locations. And there's people who their whole job is just placing the electrodes like that in is of itself is like a thing. And so the 1020 system is important because that has to do with the analysis that I've been doing. And this is where I'm just going to really quickly introduce what I've been doing and probably start to jump away from the PowerPoint and to show you my code, is that I have two projects. And so what I started for this SciCloj gathering is an analysis of some brain data. In this study, I will go ahead and I'll share it with the chat. It's this EEG data sets for motor imagery study. And it's pretty fascinating. I have to just pull zoom up here. There you go. There's the link for that. And so these people are doing a motor imagery study. And if I was actually to jump back to this PowerPoint that I showed earlier, this BCI database training here, they actually have motor imagery on here. They call that a paradigm. And so, and these are like very standardized things in like the neurological world, is like doctors really use like these categories across the board. So motor imagery, when you see motor imagery in here, it almost seems like really novel what they're doing, like because this is novel, but this is actually a very standardized like terminology that they're using here. And motor imagery is anything that is relating kinesthetic movement with neural activity. That's what that means. And so that means that this study is connecting neural activity via EEG electrical signals, and they're comparing that to movement. Now, the abstract is really fantastic. I recommend digging into it, but I'll summarize really fast and say that what they're doing is they're having people make these hand movements right here, tip of the finger, just like this, and they're charting that activity. And then, so they do 20 trials of that, and they record that activity, and then they have people imagine doing that. That's the key, is that they do another 100 imagery trials where they ask people, think about making the movement, but don't actually make it, just think about it. And that leads to a lot of really interesting results when you compare the imagined movement to the actual movement. And there's a lot of implications to like how we might apply that to other technology systems. And so I'm going to be talking about this study today. I'm just going to jump back to my PowerPoint really fast and see if there's anything else I want to say before I jump into the actual data. Yeah, I'll say just one quick thing. Actually, yeah, I'll jump into the data because once we get into the data, we're going to start talking about digital signals. And so this is brain data in Clojure. This is a Clay notebook. And I meant to share the link for this. So I'll share the GitHub link right now so you can all clone it and check it out while we're meeting here. Apparently it's not actually, I thought I had all of this stuff up before we met. Brain data in Clojure. So there's the link to this, and you'll have to go to the branch common referencing because that's where I am right now. I just pushed to that earlier today with the most recent version. And so I'll go to the brain namespace, and what this is, I'm going to gloss over it at first just to show you what I'm doing, and then we'll come back and we'll deep dive. This is a namespace that takes, we talked about it a little bit earlier, this takes MATLAB and it puts it into a Clojure map. It's very simple in that regard. That's all it's doing. It's taking MATLAB files, because MATLAB is the sort of standard for EEG recordings. And I'm just pulling that in to data, to Clojure maps. And so I'm starting the REPL. I'm going to evaluate the namespace, and you see I have load EEG data, which basically uses all the functions above. You'll see I do have these reflection warnings, and we might talk about that soon. But this is load EEG data. It's just taking this and putting it into a map. So I'll call that function now. And this used to take like 2 to 4 minutes, I was saying. But as we see, it already returned all of these pieces of data. And it's pretty complex information. I can jump in here and go to the resources, and I have the top level data structure that I've pulled apart. And this is interesting. This is pretty cool to look at side by side, in my opinion. Is we'll come and we'll look at the actual study and kind of compare these two things. So I'm going to go to GigaDB, and I just want to show you this top level data structure that I have. Now, when I first started doing this, I was like still definitely learning, and I still am learning, but I was like not confident that everything I was doing was right. But then when I got this top level data structure, I knew that I was doing everything at least somewhat correct, because I was able to pull this stuff out of the MATLAB, and it matches their data format and structure in their paper here very nicely. So we have S rate right here at the top of the map, because this map is unordered, and they actually have a different order than I have it in the map. But you see like S rate is right here. Well, S rate is actually in here, right down here. It's the sampling rate. And now the sampling rate happens to be a really non-complex piece of data. That's just an actual, they're using a double here. They're using 512. But yeah, it's a sample rate of 512 samples. So that's really good. That's like a very high sample rate. This device that I have right here has a sample rate of 200, and it's only on 4 channels. So remember that they're getting 512 samples on 64 channels. So this is some pretty high-tech equipment. You can see it's a lot of data. There's 300,000 elements in these noise recordings, 44 million in the movement recordings here, 24 million in the imagery, because this is 100 recordings. And so that's a lot of data, but this is what we're actually pulling out. And when I go into the brain namespace here, I don't pull out everything in the data structure. I just pull out what I'm looking at right now, which is movement left and right and imagery left and right. And then I haven't even used these yet, but this is sensor location. And then the other one is the sensor location projected to a unit sphere. So that's going to be cool to try and do topological maps later. Also really important is these bad trial indices, and I'll talk about that soon. But this was how I like really first knew that I was like kind of doing something right, is that I was like, okay, I'm like following along with these researchers. That's cool. And so we can go to the notebook namespace, and what we can do, because we've already loaded the data into an atom, is we'll have to evaluate this namespace, and we're gonna have to evaluate all the other namespaces. For some reason, when I evaluate this is just a weird bug I'm encountering. When I try to evaluate this namespace, it tells me that I need to evaluate, my headphones died, just a second, sorry. So this is a weird bug that I've been experiencing where it's making me actually like go and actually evaluate my other functions before it lets me evaluate all my namespaces. I don't know why that bug is happening, because like it should just let me evaluate all the namespaces from Notebook, but this works for now. And so I already have some pre-processing functions we can jump into and look at how it's working. But the first thing that I'm doing is doing some initial filtering. And while this works, because this takes about 8 seconds, while that works, I'll just really quickly jump down here to talk about the filtering. if you go down to their methods section in this paper, they talk in detail about how they process this data. And all I'm trying to do is to follow their processing, right? So I'm just following these examples, and you can see that the very first thing is that they check to see the bad trials, and they try to define which trials are actually bad. But before they even do that, they do pre-processing, which is called Butterworth filtering. And I'll talk about Butterworth filtering in a second, but let's just do this first and get some data out. We can obtain bad sample data. This is going to take a second as well. I just have some of this printing because I'm just trying to debug it here a little bit. This is a work in progress too, by the way. I have so much left that I want to do to recreate their study and to even like chart it in different ways than they do, because you can see that they actually get some pretty cool charts down here. I really love these like heat maps, and I haven't done that yet, but we're about to see what I have done. Okay, and then this is the last thing that I have to do, is just do the common average references. And so now I'm going to chart the data for us, which I'm going to come down here and I'm going to make the current form as HTML. That's how I typically do this. And that's going to go to the Clay notebook. And so I'll open that up. That's at 1971. And so this is the notebook that I've laid out here. And so you can see this International 1020 system. This is exactly from their paper. I literally snipped it. This is from their paper. This is exactly how they've labeled all of their electrodes. I just have that as a reference here at the top of the page. And below here, I have the channels. And so you can see the position of the electrode that we're looking at, and there's 4 graphs for each electrode, and we have the movement left and the movement right charted next to each electrode, and then after you go down you have the imagery events, and so we have movement and imagery separated. And there's still a lot of like organization on this page I want to do, but we can take a second to look at these 4 different charts that I have. The first one is the raw EEG output. And so I have done limited processing on this just to tighten the numbers a little bit. And I can actually show you in the code where I've done that. Is in the, is it in Signal? Maybe I can't show you. Maybe it'll come up as we talk. I shouldn't just go looking for it, truthfully. No, I think it's in trial analysis. It's right here. So under prepare EEG dataset here, this is the only pre-processing that I do to the data, is this one line of code, is this adjusted data, where you can subtract the sort of mean value across all channels. And that's just like a little bit of honing that offsets electrical interference from other electrodes, actually. So it helps to tighten the signal a little bit, is all that does. And that's what I've done with this blue bar. Now, you typically wouldn't do this yellow line, but I did it just to show. This is filtering the raw signal. Typically, you're going to want to do a couple other steps before you actually filter the raw signal. But I just did this to show the difference between the filtered raw signal and the filtered common average reference signal. And so you can kind of see that, like, this, at first glance, this looks like way more activity, but you can actually see that the scale is way different. This is like 200 max here. And when we're looking at this, this is the like actual power output. We're looking at the like electrical magnitude here of the actual, well, actually, since this is the filtered signal, we're looking at the electrical value of a particular frequency range. And so this frequency range that we're looking at, and this is where signals come into play, this is an alpha wave. And so if you recall, I have this slide here where we start talking about discrete time signals, and this is a whole world we could talk about for hours and days, and I'd love to like deep dive all of these things. And we heard about Fourier analysis and some of these things earlier today. Very fascinating and very amazing. I'll just show like really quickly a couple of my favorite things about signals really fast. I'm not going to take, I know that I don't have to speed up, but I want to show the signal processing book really quickly, just because this can be really intimidating at first, I feel like, just like a lot of things. But when we, oh yeah, so I was actually going to show this from the lecture series. I recommend this YouTube video series on signal processing. It's very amazing, and this YouTube series goes along with this textbook. Like, the book was written with the video series in mind, and the video series was recorded with the book in mind by MIT. So this is like pretty amazing stuff, and it's a great course. And we can see this function right here. I pulled up the video because like this seems intimidating, this a cos, and then this is like the alpha symbol or whatever. I forget. This is an aleph, but this math symbol, and then phi or psi. I always get those mixed up. Like, this kind of looks complicated to me at first glance, but really all this is just a cos function. And then these are variables that can be applied, or coefficients is the word that would really be applied there. And so when we're thinking about waves, we're just talking about regular old trigonometric sines and cosines. Like, there's nothing really fancy, but I do have a tendency to like assume knowledge and just like jump into really advanced things. So I'll just really quickly state the basic parts of waves. There's 3 parts. You have the amplitude, the frequency, and the phase. And so the amplitude is how high up and down each wave peaks and sort of troughs, I guess, because I'm seeing like this picture right now, so I'm using their words. Frequency is the number of times that the wave actually reverberates throughout one cycle, and we could talk about cycles as well. But then the other part of waves is the phase, and the phase is the position at a particular point on the wave in time. So those are the basic parts of a wave. And so when I pull up this like complicated looking function right here, it actually is just sine. And so I pulled up Desmos really quick, because this is like, I mean, he uses cosine as an example, but sine and cosine are 2 sides of the same coin, of course. So like, you have sine, but then 2 sine is just a transformation on that. It's just like, okay, it's a little bit bigger, right? And these are simple waves. But then like, let's take a complex wave, and well, let me just show you a picture first of just something that I think is cool. Is like this example, right? Like, you have 2 simple waves here where there's no like sort of I guess I'll call, there's an actual word for it. I'm gonna call it irregularity right now in the wave. Like, these are all equal throughout. Like, there's no actual variance in the wave at all, but you can see that these combined waves are slightly more complex. And so this is just an equation that I find like pretty interesting. Is if we zoom out here, this is a sine wave of sine waves, and I just always thought this is just a cool pattern in general. And all this sine wave of sine waves is, which is a really interesting shape, it's just a couple different sine waves. You can see the sine waves inside of them that actually compose it, and you can see that if we take the second one, that you can almost start to see how when you just add these waves together, you start getting complex waves. So these 3 waves in conjunction create this complex wave. And that's exactly what's going on with brain signals, is that we have all of these fundamental waves. And so now going back to my chart that we have in Clay here, when we are looking at these filtered signals, these yellow and green ones, what this is filtering is that it is filtering out all of the frequencies that are not considered alpha waves. So what is an alpha wave? Well, there's 4 different types of waves that are generally considered. Maybe it's 5 here. Hold on. It's actually 5. Sorry, my mistake. Alpha and beta are the ones that we're going to be mostly concerned with. And it's kind of interesting that alpha and beta are in the middle. So it kind of begs the question of why alpha wouldn't be like the lowest or the highest sound. And it's actually because they discovered alpha waves first, because they're the most common, and they discovered beta waves shortly thereafter. And then it wasn't until years later that they even thought of or discovered delta or theta waves. But these are ranges of neural activity, essentially. These are descriptions of that. So when we say 8 to 13 hertz, 8 to 13 hertz, we can actually come in, I really love this example, we can actually come in here onto the chart, and we can just start at 1 second. I'll start at like 64 seconds, right? And so since this is an alpha wave, we'll look at alpha here, 8 to 13, that means that we can expect between 64 and 65 to have 13 peaks and troughs or whatever. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, look, I'm going to be proven wrong. I'm probably counting like incorrectly because it goes from here to here. So it's probably 1, like that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It's like around there. It's kind of hard to count the complex waves, but you can see it's between 8 to 13 hertz. Now, if we turn back to the code really quickly, we can demonstrate that filtering with a different wave frequency by putting on what we'd like to see. So if we want to see beta wave frequency, we can just add that here just because it's how I coded it. We'll jump back and we'll see the beta waves. And so this is going to be 13 to 30 of those waves per second. And you can see these are very complex waves, but it would be more complex. It would actually be as complex as this top wave, except that we've extracted every single signal except for the waves that are happening between 13 to 30 hertz. And this complex wave includes all of those frequencies. And so that's how we're filtering it out. And so that's a really cool way to visualize filters and kind of how that's working. And I'll just, for the sake of showing another example, I'll put the delta waves, which are the lowest. This is between 0.5 to 4 hertz, which is not commonly recorded in humans because it's so low. And you could see this is between 0.5 to 4 actual, I don't know why I can't think of it, cycles of waves. It's not a very technical term. Okay, and I just want to see theta really quickly as well, just to do justice to the in-between space of wavelengths. And so, and you can see how quickly this renders too, by the way. This is pretty intense data. Okay, and so what's happening here, you see these like really big signals. This is from some edge interference. So we can actually get rid of that. I'll probably just have to come up here, and it's kind of weird. I haven't looked at the theta waves too much, so that just might be a little bit more affected by interference on the edges. And so if I might be able to just do like 2. I'll see if this fixes it. It might not, to be honest, but let's just give this a shot and see if it makes that a little bit more easy to view. Yeah, see. Oh wait, well that was that one. It didn't really help. Well, this is between 4 to 8 in a second, which it's probably true. It's just that these are like really faint signals, and it's because there's not a lot of theta. It just goes to show you that there isn't a lot of theta activity going on in a conscious human being. It's mostly activity happening in alpha and beta wavelengths. That's why the magnitude isn't very great here, but you can see there's probably between 4 to 8 actual cycles in a second, or phases. Okay, so that's some basic signals.
Lorelai, maybe I'll stop you for a moment. And just so that you can rest for a moment, let your voice rest. And we are about 1 hour after the beginning, and I'm so glad that this is continuing. And we got to hear all that. And actually, to be honest, uh, I think that's one of the best explanation I've heard of what alpha waves are and what a band of frequency actually means. That's what was so helpful, I think. Maybe it is a good time to think about time, about to be a bit planned about the coming part. Oh, I know you have a little more to tell, and maybe you could kind of think about how much you wish to keep going. What do you think? Yeah.
I think that that's an okay stopping point for this, but maybe I'll shout out my like coming project for
I think,
Clojure.
yeah, I think maybe we are, in a way, we are at the core of where we hoped to get in terms
Yeah.
of the analysis. So I think if you can, if you have a little more time, it would be good to continue a little bit, but maybe be a bit more minded about the planned continuation. You know, are we hoping to continue like 10 minutes or 15, or, you know, depending on what you're planning to show, just so that you can.
I've definitely said a lot of the most important things. Yeah, I got through everything in the slides that I wanted to get through for the time being. But I definitely did want to just take a second to talk about what I plan on doing next. Let me just take a look at the data in here really quick. So, I mean, yeah, we definitely covered like frequency bands and filtering a little bit. Right now.
So just to be sure, when you say filtering now, did you mean the frequency band or another notion? I'm maybe unsure about whether you introduced filtering.
Yeah, that's how we were seeing those frequencies isolated, is that I was filtering them with the.
Oh,
Yeah,
you
that's
mean,
what we.
yeah, you
That's
mean
what we were going
frequency
to. We
band.
were going to talk about Butterworth filters. That's what I
Yeah,
was
I was
going to.
wondering. Yeah,
That's
thanks.
what I was, because I hadn't aptly described Butterworth filters to you before, but like it's actually pretty simple, and I recently described it totally wrong. So if there's anybody here who was there when I last described this, I apologize for feeding you wrong information. Because last time I said, oh, it's like something about reflections. This is why Butterworth is good. No, the reason that Butterworth filters are used to do the sort of filtering that I just showed. Let me just go back to it really quickly. So this is done with a Butterworth filter, and the reason why a Butterworth filter is chosen to extract these frequencies in particular, because you could use other filters, but the reason why is easy to show visually. This is the reason why, is that there's these, it's called ripples, where it like kind of goes down and it'll like bottom out and then bounce back up, and there's like kind of like a little bit of a bouncing motion with elliptic filters, with Chebyshev filters. These are just different methods of filtering, and you can see
Maybe we should explain what this plot was. I mean, you shifted to the frequency domain in that plot, so maybe that's kind of new and worth commenting about.
Yeah. So this is basically like showing how the extracted signals are cut off in particular. So when you define a frequency range for a filter, I mean, first of all, there's several different types of filters, but they're not that complicated, truthfully. There's like high pass filters, low pass filters, and band pass. High pass literally means that you allow through the high frequency information and you filter out any low frequencies. Because remember that when I was talking about it mathematically here, there's like higher and lower frequencies that compose the complex signals, And through advanced computation that is all encapsulated for us by brilliant programmers, we don't have to worry about that. We can just call the filter function and it does it all for us. It breaks it down into the component parts and it returns for us the sum, or the actual convolution, maybe is a better word, of all of the different remaining simple waves. And it presents to you, again, that complex wave. And so when we're talking about these filters here, what we're filtering out is any simple wave that composes it at too high or low of a frequency. High pass filters let through high frequencies, low pass filters let through low frequencies, and a band pass frequency will only allow through frequencies that are in a certain range, essentially. And so there's band pass and band stop filters, and those are two ways of cutting off different frequencies. But when we say that the frequency is like quote unquote cut off, it means that there's a different sort of sharpness to which it cuts off those frequencies. And so if something is closer, it's like a weighted filtering. And if something is closer to the range of accepted frequencies, then it's going to be filtered out of that last wave, the final product, a little bit less. And so this is just comparing a couple different waves. They're kind of weird charts, but I thought they were like kind of good looking. You did point out that this is a different type of chart. Basically, this is showing the frequency response to the actual filter itself. And so what a Butterworth filter does is it presents for us, quote unquote, the maximally narrow frequency band. And so, like I said, with all of these other ones, there's some like really weird like rippling that happens with these. And not all of them are as smooth. You can see that this has like this, it's not a very good chart, to be honest, but Chebyshev filters have this like very like sharp kind of cutoff here. And when you look at a Butterworth filter, it's maximally flat, which means that it's going to have the least like narrow temporal variance. Everything is going to be like a lot smoother with a Butterworth filter than it would be with any other filter, which is really great for brain activity. It's just really helpful for charting this kind of information. Oh, this is another really interesting thing. This is called a notch filter. And I just think that this is beautiful. That's why I included this. This is notch filters are really great for extracting one particular frequency. And you can see that here at 1, it's basically saying we are looking for one frequency. And so filter out everything that isn't 1. And it's doing it in this weighted way. And so this pulls out particular frequencies. I'm not using a notch filter anywhere in my program. It's just an interesting aside. Okay, so that's filters. Hopefully I did an okay job of describing that. That's how we get this. There's a lot more in the future that I want to do with this. In the future, I want to recreate all of their charts because I haven't done quite that yet, you know. I'm on the way to recreating these left and right hand like overlaid with one another, but I haven't exactly done that. And they are doing this to show a very particular brain activity, which I won't really get into, but basically they're saying that when you do things with the right side of your body, there's a certain response in your brain that happens on the left and the right side in a different order. And when you do it on the left, that order is reversed. But in both cases, there's activity throughout your whole brain with left and right hand movement. It is not like the right hand side of your body is associated with only the left side of your brain. That's basically one of the main things that they're showing, is that like there's activity in both hemispheres of the brain with any motor activity. And then the further point that this study is trying to make is that there is a correlation between imagined kinesthetic activity and real recorded neural activity. So that means that if you imagine yourself making a movement, that the actual recorded electrical signal does indeed match the recorded kinesthetic activity up to a certain point of accuracy. And they do go through those rates of accuracy in here pretty thoroughly. And I think they found somewhere between like 76 to 84% correlation between the imagined input and the actual performed kinesthetic activity. And I would like to show all of this with my research, but I do want to be conscious of time. I've already talked for way more than I was even supposed to at first. I'll close with just one last thing, which is that since I was able to crowdfund this device, which I can't even like emphasize how awesome it is, it's been a dream of mine to have one of these for a long time, and a bunch of people in the Clojure community helped me to do that, and I'm very thankful to all of them. I now have the ability to actually do brain computing out of my own house, and I can take these EEG signals and I can record them and do things with them that are like really, really interesting. And so I, for one, I'll just show you a real quick demonstration. I have this recording now. You should be able to see the flashing button. I turn this on, and it's not connected to anything, but it connects to my computer via Bluetooth. So like I don't need to actually connect it into my computer to pick up these EEG recordings. I can go to the visualizer that I made. It's down here somewhere. It's down here at core, and there's kind of some junk in here. Started project REPL. This should not take long, and this will be like kind of what I close on, I guess. Is just I'm in the process right now of actually starting to record live brain data at home, which is just like incredible. And this is going to become more commonplace for all programmers. And I'm doing something that a lot of neurologists are not doing, which is pretty amazing. Oh, I evaluated it without actually evaluating the namespace. It's going to fail. Just a second while it tries to fail. Okay, it's working. It pulled it up. Okay, here it is. Ready? This is my EEG brainwave visualizer. And so this is currently taking samples from this device live, and you can see it stop flashing because it's actually connected to my computer now. And it needs a certain number of samples to actually perform Fourier transforms appropriately. So that's why it has to calibrate. Now in the future, I'm gonna have it write these samples to file, so you'll only actually have to calibrate it this way once ever, and then it'll just have those former calibrations. But I haven't set that up with this visualizer. That actually is set up in the back end, and any programmer could download my Clojure code and run this with pretty much any on the market brain chip. And so we'll see that once this reaches 256, that we'll start getting frequencies. And furthermore, and this is probably the crux of everything that I'm doing, is that this visualizer will show you how normalized I have these frequencies. And so ideally, I'm performing like on the fly adjustments to these numbers to keep it as stable as possible. Typically, if you were recording these, the numbers would be going all over the place, but I have used Clojure to keep these bands purposefully in as narrow a frequency as possible. That way, when I hook this up onto my actual head, that it detects extremely minute parts of electrical activity in my brain, and I'll be able to issue commands to my computer very effectively with only 4 channels of information. And so this is extremely exciting for me. This is just the start of like everything that I'm doing. I could talk about it more. You know, when I actually said that I needed to write to file, it actually is writing to file, believe it or not. I can show you this resources. It's under recordings here. So you see I already have some recordings in here. So once I go to the WebSocket namespace, come down here, and I'm gonna do stop and save. I'm just gonna evaluate this, and oh, it didn't actually stop it, but it did save it. We'll see a white folder here, and oh, well, actually, Did it save? Let's make sure it saved. Well, actually, maybe that one's not working because I did change the code a little. But all right, I'm stopping that. And well, yeah, I guess I'll end there. I'd love to show you more of like the API that I'm building to take this actual brain activity. But this is like the other thing that I'm really excited about. And I'll be talking about all of the things I talked about today in a way more condensed and well-prepared manner and without background noise in about a week at Clojure. And that is only in person, unfortunately. So you'll have to watch the YouTube video if you're not actually there. But I highly encourage you to watch that Clojure talk because I'll be talking about all of this stuff. And in particular, I'm going to be talking about this API that I'm building. This is called BrainFlow. The BrainFlow API is what lets you interface with this hardware, and I am building a Clojure wrapper around it. And so these are the current commands that you can issue with the BrainFlow API, I'm calling it. But it's still a work in progress, but you can record data and stuff. And so I've shown that to you all now slightly, and I'll stop. I could talk about this stuff forever and ever and ever, obviously. So let it go.
Thank you so much, Lorelai, for taking the time to tell us all that. Yeah, maybe just thinking about the hour, maybe everybody here may need a short break before we continue. This was a great talk, and if it makes sense, we can chat a little further and maybe have some questions to Lorelai if anybody wishes to ask anything. So should we take like 5 minutes break and continue a little bit with a few questions? Is that it?
Sure. I'm very into the idea of a break really quick, and I'll just be back in a couple of minutes.
Sure, thanks.
Sure.
Yeah, so we're back recording for a little bit, following up on Lorelai's great talk. And now we have some time for questions and thoughts and conclusion of this talk, which was the last of the day. I really liked how you make the big picture part of your story with the ethical introduction and this reading into the old writings, which was kind of important. And this critical view of your own work is, I think, it is great inspiration.
Thanks. Yeah, it's definitely really important, and thank you for giving me, I meant to like just offer more thanks to everyone for listening and for you to give me the opportunity to talk about it.
Yeah, and maybe one thing that was actually, in a way, huge news for us was that you're showing us how you do data analysis on the fly with an actual device, which is something that we just don't do so often, right? And it is just that most of what we do is with offline static data sets. And now it is live, and it changes so much about the mindset, about the mode of work, as you have been explaining to me in the last few weeks, I believe. And that's big news for us, that you're opening this new path for us with this project.
Yeah, and I would like to know the drivers needed to drive these this device. Did you write the drivers yourself? Are they in Clojure or?
The firmware and everything comes pre-installed on them, thankfully, and it works very well. And they also offer instructions for how to like hack that yourself. It's all open. Like that's one of the reasons that it's called OpenBCI, is that it's a completely open source initiative all the way down to the hardware. They have the schematics on the website as well, and the creator himself is on Slack and has an active BrainFlow Slack. And I haven't told them that I'm doing this, but I plan to soon. I just want it to be in a better shape before I tell them, basically.
Mhm.
Yeah, so I didn't have to worry about that.
But then,
Thankfully.
how do you get? Do they have Clojure interfaces or Java, or how do you?
Yeah, I kind of glossed over that. That's what I'm doing in Clojure, is that I'm actually using their Java interface, and their Java interface uses their C++ code. And so, yeah, they are actually running C++ like at the very bottom of it. And I might eventually even kind of like jump into the C++ myself instead of Clojure, just to like get basically down to the metal for certain parts of the process, because I'm doing something pretty cool. The thing I'm most excited about this is less with the hardware and more with the file system that I've been building around the device, because I came up with my own file system of binary data to represent the EEG waves, and so it's extremely cost efficient. Like, these MATLAB files are hundreds of megabytes, and I'm recording on binary data files, and I have each recording is, I should have gone into this more. I'm going to talk about this at Reclosure in depth, but each recording is a folder, and the folder contains one file for each channel, and all the files are binary except for a recording metadata file, which has useful information about the wave that's been encoded in the file. So right now it just has like the mean frequency, so you can just access the mean frequency from this binary file of the wave, like in the actual binary header. And so it's filled with like a lot of useful like front-loaded data like that, and that's where like my interest is, rather than the firmware, is like coming up with this generic file system that allows really low cost EEG recording, because people are going to want to leave the device on for hours and continue to record brain data. So we need to have a really, really low cost way to store it. And I think I came up with about as low a cost of way on like a binary machine that you even could, because thus far the recordings, like I'll record myself for like 3 minutes at a time, and it'll be like 7 to like 20 kilobytes of data, as opposed to like hundreds of megabytes of MATLAB files. And I'm planning on trying to build a conversion code to switch my file type to MATLAB, so that anyone will be able to read these files into MATLAB, and then kind of like interop between just the EEG recordings. And so that's just a really exciting thing that I just started talking about because I'm into all of this. But yeah, drivers, didn't have to worry about that. I might in the future, but it would only be for fun if I did that. That's not like a main thing I'm working on.
Impressive. Thanks
Have
for
you
us.
have you done like embedded systems programming yourself, might I ask?
No, I did some driver implementation during my studies, but that was it.
Can you
But,
talk about that?
uh, I worked for a care, how would I call it, for an institute at the university where I was, and they were doing AI research, and that's almost 20 years ago. And we had to implement protocols in Java by looking at how they're done in C++, and we had to kind of attach to some devices, and had to write drivers for that. So, but it's 20 years ago. I was just wondering how you did
Yeah.
it yourself in such a short.
Yeah. Oh, well, I've also been like, it's honestly like a dream come true. I've been thinking about this project for a really, really long time. Because honestly, if I'm just like bearing myself to the group and to the world in general, it's like I grew up in a situation where I like had access to in a certain way. you could say that I was like spoiled technologically for sure. Like I had access to computers in a way that a lot of people didn't. And for me, it was never enough. Computers have never, ever been enough for me. I've wanted the experience of computing to be as tangible as possible. Right beside me, I have like a really nice touchpad that I shelled out like more than I can afford, just because like the experience of handwriting on a digital object is like really important to me. To be able to do that, it's the only way I can freely think on a computer is to handwrite. And so like brain computing for me represents what I've always really wanted to be able to do. And Danielle, earlier you brought up Clojure, Python, and like that is something I've been like, I can't believe we haven't even talked about that, because Python, or well, yeah, Python, Blender is what you're talking about. Python Blender with brain computing is something that is one of the reasons I started down this path. I would really like to 3D model with my brain. That to me represents the one of the forefront innovations in all of computing. Would be able to create worlds. But that's really far away. That's pretty far. And I'm not very good at 3D modeling. You still have to be good at 3D modeling in order to do that. You still have to know about like models and textures and all of those things, but it's all fascinating. And you know, just to bring it back to the ethical part too, because the ethical part is so important to me, is that to me, the world is so grim, and there's obviously so many problems. And I think that this is one of the few solutions, is this technology, because it's becoming much more affordable, and it is something that will give a lot of freedom to individuals in a lot of ways, but it's also a way that it could be used to enslave people as well, and that's important to like be aware of and to legislate around. I don't know if legislation even exists in the world that we're going into, to be honest, and I have very little control over what world we enter, and that's why I'm just trying to make this technology as fast as possible. But to me, this seems like a reason to hope for the future, and so that's one of the reasons I cling to it so much in general. And
for saying
also,
that.
sorry, what?
Thank you for saying that.
Definitely.
About
Sorry, I didn't mean to cut you off. That's just like the Zoom lag. It just like makes everything harder. But definitely that's a big part of it. And I can't emphasize it enough, basically. But then at the same time, I try not to like get on a soapbox or anything, to be honest, either. But yeah, thank you for the question about the drivers, because that's a whole nother. I could just go on for days about every aspect of the technology. It is so, so fascinating. I'll just really quickly, can I just share my screen for another second? I won't go off the rails. I'm just going to do this really fast. I just want to show you the actual website, the OpenBCI website, because their docs are just so fun to look at. And you can look at they have software, firmware, and hardware stuff. So you were kind of asking about the firmware, but I just think the hardware stuff is so cool. And this is what I meant about them publishing the specs. They have like all the layers of the board here, and you can get the Gerber and Baum. So it's all right here, and the GitHub is up there. They have a pretty responsive group. You can see these were the things that were on the board. And so AVDD is actually the power supply, I guess. Okay, so very cool. Yeah.
maybe it is a good moment to say goodbye to the recorded part, unless you wish to
Sure.
say any concluding words, Peter or Lorelai, before we close the recorded part.
I feel like I've spoken enough.
Oh, yeah, that was amazing. Yeah, thank you so much for this talk and discussion. And so we will say goodbye to the recording and maybe keep chatting a little bit, and see you, to our friends, tomorrow, probably.